rational relationships. 3.2 is what we're starting today. Just preloading this a little bit, giving you a little sneak preview. Simplifying rational expressions is similar to simplifying fractions. Okay, multiplying, dividing rational expressions is similar to multiplying and dividing fractions, and then adding and subtracting rational expressions is very similar to adding and subtracting fractions. So if you like fractions, then you're going to love this section. But that's a joke because no one loves fractions. I'm just kidding. I'm sure. Well, maybe. I doubt it though. But it's going to be the same rules that you've gone over in the past: common denominators, like terms, factoring certain things out, dividing them out to simplify a fraction. So that's what we're going to be focusing on. So let's review a little bit of the stuff from yesterday. Polynomial expressions, if you remember, it's just anytime you have, if there's a power to it, it's 0, 1, 2, 3, or so on. It's not negative, it's not a fraction, and they're separated by adding and subtracting. That's what separates terms for a polynomial. Polynomials, all exponents, 0, 1, 2, 3, and so on. You can't have negatives or fractions. If you were dividing by a polynomial, it's not a polynomial. It's a rational expression. We'll go over that. Or we're going over that this entire unit. This one right here is a rational expression. This one right here is a rational expression because technically that y to the negative 1 is on the bottom. The denominator you're dividing. This x to the negative 3 is on the bottom. To be x to the third because it's negative. But we'll talk about that in more detail. So rational expressions, it's just a ratio of two polynomials. So you have a polynomial divided by another polynomial. Okay? And if you set that bottom polynomial equal to 0, it can help you find vertical asymptotes. Okay, if you set the entire thing where x is going to infinity and work it out, you can potentially find a horizontal asymptote if there is one. And that was what 3.1 was all about, rational graphs. So the graphs of rational functions. Okay, graphs of rational functions can have asymptotes. Not always, but they can. The ones that we're going to focus on in 3.1 will. But they're not going to be slant asymptotes like this. They're going to be vertical asymptotes where they go up and down. And this occurs wherever there's a division by 0. Okay. Which is basically what it's, well, it doesn't really say that here, but it's saying that the y is going to infinity or negative infinity. If you notice, the y is going up here, infinitely, and then this one is going up here, infinity, and then negative infinity down there. Okay. To find vertical asymptotes, it occurs at x values that cause a rational function to evaluate to a non-zero over 0. Okay. That's what you're looking for every single time. If it's a 0 over 0, it's a whole. But if it's a non-zero over 0, it's a vertical asymptote. So if you look at this example right here, 3 over x minus 1, you just set x minus 1 equal to 0 and solve. And if you notice, the vertical asymptote's at x equals 1. Wholes is when you have a 0 over 0. So for example, this right here, if you plug in a 1, you get 0 on top divided by 0 on the bottom. So there's a whole at x equals 1. Okay, horizontal asymptotes are a little different. And if you notice, the x is going to infinity. Okay, if you follow this rational function here, the x is going to infinity or negative infinity. It doesn't matter which one you do. But you can use limits because you can force x to go to infinity or negative infinity, and you can use that to find horizontal asymptotes if they actually exist. It is important to note that they do exist if they actually are going to some specific value. If you notice, this one is going closer and closer to some value. It's not going to infinity. It's not going to negative infinity. It's going to whatever this dashed line is. Okay. It is a horizontal asymptote when x goes to infinity or negative infinity. The curve approaches some constant value b. I kind of already said that, but here we go. We have this going closer and closer to some value. It's never going past it. It's just getting infinitesimally closer to it, but never actually reaching it. That is what a horizontal asymptote is. Okay, rational expressions. So the first thing is all about simplifying them, and the easiest way to teach this is just through an example. So that's what we're going to do is I want you to write this down in your notes, and we're going to try to simplify this. And we're going to simplify it just like we would simplify fractions. All right. So before we start with this, I do want to kind of go over simplifying fractions real quick, just so you can kind of see the parallels between these two things, these two concepts. So let's say that we had some fraction like, I'm just going to use a super easy fraction like, I don't know, 2 over 4. If you factored the top and the bottom here, you would end up with 1 times 2 over 2 times 2. And 2 over 2 is 1. So what you can do is simplify this by going 2 over 2 is 1. So that cancels out. And you're left with 1/2. Okay? This should be a review. You should know how to simplify fractions. This is the exact same process that we're going to use to simplify this rational expression right here. Okay? We're going to factor everything first, and then see if anything cancels out. Once we figure out if it cancels out or not, then we have the answer. Okay, so let's do that. If you notice this top part here, this v minus 5 is already factored, so we do not need to worry about factoring that. So I'm just going to rewrite it here. It's going to be equals v minus 5. Okay, but we do need to factor that denominator there. V minus 5 times v minus 5, or you can do v minus 5 squared. It doesn't really matter. Okay, now just like before when we did 2 over 4, we canceled out the 2's. We're going to cancel out v minus 5 because that's technically a number. In v minus 5 right here, and you're left with 1 over v minus 5, and that is the final answer for this. Let's do another one. Okay, step 1, just like simplifying the fraction, is to simplify, or when we're simplifying the fraction is we factored everything. So we need to factor things here as well. So the x plus 6 is already factored. So I'm just going to keep it like that. And then we have to factor the bottom. What does the bottom factor to? X plus 6 and x minus 1. Okay. By the way, if you forgot how to factor this, you're looking for two numbers that multiply here and add here. Okay. 6 plus negative 1 is 5. 6 times negative 1 is negative 6. Let's say you forgot how to factor. Just use quadratic formula and you'll get negative 6 and 1 for the answers, and then you can use that to create the factor form. Here we have the x plus 6 and x plus 6. They both cancel each other out, so it's 1 over 1. And your final answer is going to be 1 over x minus 1. And if there was a vertical asymptote on this one, x is equal to 1 would be the vertical asymptote. The horizontal asymptote for this would be 0 because you're doing 1 divided by infinity minus 1. But it doesn't ask for that. I'm just asking you to simplify. All right, onward we go. All right, multiplying and dividing rational expressions. This is similar to multiplying and dividing fractions. But the easiest way to kind of show this is through an example. So that's what we're going to do next. If you notice, I have two fractions here of polynomials. So it's a polynomial over a polynomial times a polynomial over another polynomial. Okay. And if you remember, a polynomial divided by another polynomial is called a rational function because it's a ratio of polynomials. We're going to compare this to multiplying fractions. So let me just make up a problem really quick for the fractions. Let's go with, we'll do 2 over 4 again, times, let's see here, 1 over 6. It doesn't really matter. Okay. What you can normally do for these is just multiply across, but I highly advise factoring everything out first. Okay. So the 2 over 4 is really just going to be a 1 times 2 over a 2 times 2 times 1 over 2 times 3, because 2 times 3 is 6. Okay, now from here, you can simplify things out. If you wanted, you can even cross out this in this. That is completely legal when you're multiplying. In hindsight, I wish I did like a 4 here. So let's make this a 4 instead. Okay. And the 4 would have broken down to a 2 times 2. 2 times 2 here. And what you could have done is simplified this as well. You can do directly underneath it if you wanted, or you could go across. It doesn't really matter. As long as there's something on the top and something on the bottom, that's the main thing that works with this. And if you notice at the top, I have 1. These are all 1s here. So it's 1 times 1 times 1 times 1 is equal to 1. Okay. And then over here, it's 1 times 1 times 1 times 3. So your final answer should be 1/3 for this. Okay. Here's another little trick that some of you probably already know. Hopefully you've got a teacher show you this. But this is technically 4 over 4 here. So you can do 1 over 1. And then do 2 over 6. We'll divide this by 2, divide this by 2. And you get 1 times 1 over 1 times 3, which is, again, still 1/3. So you can use all those same tricks with multiplying and dividing rational expressions. Okay. So step 1 for this would be to factor everything out as much as humanly possible. So we're going to do that real quick. X plus 7 is already factored, so I'm just going to rewrite it. What can I factor out of this? Whoops. Out of this thing right here. What can I factor here? Anybody? What's the 7? Right. So factor out of 7, you get 7 times x plus 5. Okay. Times, now we have to factor this quadratic up here. So you have to think, what are two numbers that multiply to get -40 and add to get -3? Multiply -40 add to get negative 3. When in doubt, just write down every single two numbers that multiply to get negative 40. So we have 1 and negative 40. That's not going to be anywhere near negative 3, so we're not going to worry about that one. 2 and negative 20, again, not near negative 3. 3, 4, let's do 4 and negative 10. That's negative 6, nope. All right, let's do 5 and negative 8. Uh-oh, 5 and negative 8. Those multiply to get negative 40, and they would add to get negative 3. So we're going to factor this to x plus 5 and x minus 8. Okay, and just like with the fractions, we can start simplifying things out. X plus 5 over x plus 5, that cancels, so it's 1 over 1. X minus 8 over x minus 8, that cancels. And you're left with x plus 7 over 7, and that's your final answer, essentially. X plus 7 over 7. A rational expression is considered completely simplified if there's no other common factors in the top and the bottom. So it's similar to how a fraction is when there's no common factors at the top and the bottom. Then you know it's fully simplified. Let's do another one. This was multiply, so this one's going to be divide. And basically dividing is the exact same thing as multiplying, only there's one little difference when it comes to rational expressions. Like say I did 2/4 divided by, let's just do 4/6 again. You covered it, I believe, in, I believe it was middle school. All right, so for this one, the shortcut is to multiply by the reciprocal. So you change the divide by to multiply. So you change this, and then you have to flip this to be 6 over 4. Okay? And then you're going to want to simplify things as much as possible. So this is 1 over 2. This is 3 over 2. You multiply across here, and you end up with 3/4. Okay. It is the same exact rule for dividing rational expressions. You want to multiply by the reciprocal. So right away, what I would do is change this to a multiply and then flip this. So you're going to end up with b squared minus 2b minus 15 all divided by 8b plus 20 times 4b plus 10 over 2. Okay. Now it's the same thing as a multiplying rational expressions problem, only we have to, factor it like we did last time. So factor this top part right here. You're thinking of two numbers that multiply to get negative 15 and add to get negative 2. Anyway, so this is going to be negative 5 and positive 3. So b minus 5 and b plus 3. And then we're dividing this by this part right here, but you can actually factor a 4 out of there. So that's 2b plus 10, 5. That's embarrassing. Okay, and then over here, the 4b plus 10, you can factor out a 2 on this, and you get a 2b plus 5. And then we're dividing this by 2. Okay. You can see a ton of things, not a ton of things, but a bunch of things cancel out here. This 2b plus 5 cancels with this 2b plus 5. This 2 and 2 cancel here. 2 over 2 is 1. Okay. And the b minus 5 and b plus 3 don't actually cancel out with anything. So I'm actually going to put those back together, which is where we started, and divide it by 4. And that's the final answer. Okay, one thing I do want you to notice on this one is you're dividing by 4, so that means it's impossible to have 0 on the denominator because 4 is on the denominator. There is no 0 possible in there because there's no x. If it's an x minus 4, then you could, but there's no x. So there is no vertical asymptote on this. Again, trying to compare it to the stuff that we went over in the last section. All right, so we are going to go over the last subsection in 3.2, adding and subtracting rational expressions. And again, it's a polynomial divided by a polynomial. That's what we have here, only we're adding them together. It is the exact same rules as adding and subtracting fractions. You have to have common denominators, so that is definitely the goal that you're going to want to have for these is common denominators. Let's do an example real quick, I guess, to over this. So say you did, I don't know, 2 over 4 plus 4 over 6, just because we're using that same example each time. You need common denominators here. You don't have that right now because this one's a 4 and this one's a 6. So one way of doing it, it's probably one of the more easier ways of doing it, is if you just multiply this one by 6 over 6 and this one by 4 over 4. Because if you notice, here, let me highlight it, the denominators are now the same. So now what you can do is you can just say, hold on, you can do 2 times 6 plus 4 times 4. That's supposed to be a times. It looks like 4.4. All right, I'm going to actually just write the number out here. So 12 plus 16, and then you're just dividing it by 6 times 4. Okay, I'm just going to write 24 at the bottom. What some people do is they'll do this. They'll do 12 over 24 plus 16 over 24. Well, you already know they're common denominators. Why have them separate into 2 separate things? Just combine them into 1 right away. Okay, that's what I would do. You can do whatever you want, but highly recommend doing that so you don't have to write things a bunch of times. Okay, now from here, you end up with 28 over 24. And then obviously you could simplify this fraction by breaking it down into its factors. They're both divisible by, let's just say 2. Okay, but you can also, so that cancels, but you can also break down the 14 to 2 and 7, and the 12 to 2 and 6, cancel that out, and you end up with 7 over 6 as the final answer. Okay. Now you don't really need to know, like, I'm not going to be ever asking you for a fraction to add those fractions, but you do have to understand the common denominator aspect of this and then combining at the end. So that's what we're going to use on this one here. So the easiest way to get common denominators on this is to multiply the denominators by themselves. Okay, there's nothing that simplifies here, so that's your best bet, is I'm going to multiply this first one by x minus 2 over x minus 2. And then I'm going to multiply this one by x plus 6 over x plus 6. Okay. If you notice now, our denominators are the same. So because they're the same, I'm just going to, this lets me, I'm just going to rewrite the denominator down here. So it's going to be x plus 6 times x minus 2. That's the denominator. And then I'm going to multiply these two things together. So it's going to be 3x minus 6 plus, I'm going to put parentheses on that, plus we're going to distribute the 7 to each of those terms there. So it's going to be 7x plus 42. Okay. Any last step is to just simplify everything, which is what we did in that, that first section we went over today. So we have 3x plus 10x. Oops, sorry, plus 7x is 10x. And then we have negative 6 plus 42 is 36. And then we are dividing this by x plus 6 times x minus 2. Now, if you wanted to, you can expand out that bottom part. I'm not really worried about that so much because, I don't know, it's not really part of the problem. There's nothing that can factor here and cancel out, so this is actually your final answer. There's no common factors at the top and the bottom that can make this any more simplified. So that's basically it. So that's basically all of 3.2 in a nutshell.